us with wonderful stories about hydrology and the soil model. And I hope you guys can stick around for as long as he wants to talk to us. So, go ahead, Lloyd.
I may drag on a little bit, I'm sorry.
That's okay. You've got our time, Lloyd.
I've been impressed over the years with at least two series of experiments done at Coweta that have had the effect of rewriting textbooks. One, of course, was the cutting of the vegetation of watershed 17 and several other watersheds that came up with the results that were entirely opposite from what conventional wisdom would have dictated, and really caused, a change in the way people thought about managing forest land. The second was the soil model. I'm not knocking anybody else's research. I'm just thinking about these are things that really kind of undermined the way people were thinking and caused them to have to think it over again. And in the case of the soil model, it started as a persistent concern on the part of John Hewlett and activity here at Coweta that was directly in opposition to the instructions that he got from Asheville. They were told not to do that experiment, but he did anyhow. But the conventional wisdom and what you find out in flat land is if rainfall comes in here, it establishes some sort of a water table on top of bedrock. And if you dug a hole here, you'd find a water table. If you went over there, you'd dig a hole, you'd find a water table. And what we tried to do is to push that water table up the slope and say, okay, the rain comes in here, it runs into bedrock and it establishes a water table and it flows down to the stream. Well, if you go up on the hillside anywhere except right next to the stream and dug a hole, you'd never find water. And that bothered John Hewlett. He worried about that, and he stood out in front of watershed 17 and he looked at that thing and he said, where in the heck is all that water coming from? And what we're concerned about is that that water comes into the soil and it must follow some pathway, but it's not scooting along bedrock, and there's only a water table down next to the stream. So let's build a box. The box is going to be kind of an array of soil reaching from the stream all the way to the ridge. We're going to fill it full of soil. We're going to put water on it, and we're going to see what happens. The bottom of the box was just a concrete cave here with 3 outlet holes in this case. This was a bottom drain. We found out we didn't need later on. This is an overflow drain. Again, we found out we didn't need. And this is the main outlet, which essentially established the level of the stream or the water table. We piled, if you dug into a stream channel, like you were getting ready to build a weir, you would find that you went from a bunch of rocks to some gravel, to some sand, to some soil as you went up the hill. And so this is what we put in the bottom of the soil model. We have a screen here to keep stuff out of the drain, and we have rocks, gravel, sand, and mixture of sand and soil and so on, until we finally got the same sort of thing that we see out in nature. The soil was sieved and then packed to the same bulk density that we would find out in the watersheds. The reason we sieved it is to take out any rocks and roots. We wanted to deal just with the soil effect. You can see here, we piled the stuff up, provided a water table, and then we had some various instruments up the slope. We had neutron meter access tubes to measure soil moisture. We had tensiometers to measure the tension at which water was held, and piezometers This is just a tube that comes down here and comes into the bottom. And if there's water standing in the bottom of this box, it would show up on the tube. So we were looking for this question of, does the water scoot along the bedrock? These things were arranged in stacks as we go up the slope, so that we were able to get our information both relative to depth and relative to distance above the water table. We caught the water in this high technology container and measured it with this high technology FW1 water level recorder. You know, these are the days when you couldn't buy electronics. You didn't have any money. But when it got down to the dribble stage, we used another technology here, a rain gauge, smaller volume, and again, measuring it on a chart recorder. After the soil was packed in the model, it was sprinkled with water, bringing it up toward, but not to saturation. We didn't want it to all come sliding out of there, but we were able to get it pretty well gone wet. Then we covered it with plastic. We didn't want to have any evaporation. We just wanted to deal with the water moving through the soil. Here's a neutron access tube, and Ron Hibbert there is determining the soil moisture content. In other words, what percentage of the mass was water, what percent is soil. The local meteorologist, a fellow by the name of Swift, had to have some meteorology, although he couldn't really explain why, so he's got a hydrothermograph. It later turned out to be a good idea, but he didn't know that at the time. That was done in June of 1959. By August, we determined that the first model we built wasn't long enough, so we knocked the end of it off and added another 8 or 10 feet to it and continued on. There was another model built later on that same year, or the next year. They all had essentially the same sort of response. This is a log-log curve, and you can hide anything behind a log-log curve. This is 1 day, this is 10 days, this is 100 days, and this is the flow that's coming out, and we've got one characteristic flow rate that occurred in the first day. And then it kind of fiddled around here, and then it established another curve that lasted for the next 150 days. We'll talk about this a little bit later on, but this is what John later came to call quick flow and delayed flow. This is the immediate response to the storm. This is the slow response to the storm by the water that is stored in the soil. Okay, this is moisture content again. This is moisture content over time. Again, 1 day, 10 days and 100 days. And this is at or just above the water table. Doesn't change much with time. And then you drop down 4 feet or go up 4 feet above the water table, and you have a much lower moisture content, but also one that declines with time. And if you go up still further up the slope, you've got another curve. But look at the nice data you get with a log-log curve. All right, this is, I'm sorry, I apologize, piezometers. Those are the things that just show the height the water is standing in the soil. This is 9 centimeters, 9 centimeters above the water table, and the water doesn't stand in the piezometer much after the first day. if you're above the water table, that's about 300 centimeters, I believe, you don't even get water standing in the piezometer even for a day. In other words, it was only when water was being sprinkled on the machine. And that answers the question: water does not come in, go down to the bedrock, and scoot along the bedrock. Something else is happening. These others are the soil moisture tension, and the bigger the tension, it's a negative number, so it comes out the wrong way on the scale. This is 400 centimeters above the water table. This is at or near the water table. Of course, the tension is very low or negligible or positive up at that moist place. But everywhere else, the tension begins to build up. In other words, there's a strain between the water and the soil. So we did learn some things from this. I'm going to cheat by getting my little words over here. But we found that there was no universal water table on a slope. That was new information. And moisture was only in the area next to the stream. And the moisture content and the energy that is used to hang on to that moisture increases or decreases as you get above the water table, and it also increases with depth at any point on the slope. We developed the idea of quick flow and delayed flow, and we'll come back to that later and show how that has been applied. Even without the plant cover or evaporation, there was this gradient with depth. Now, that business of putting a hydrothermograph out there, it was hard to justify even putting it out there. But toward the end of that declining curve, I don't know whether you noticed, but the data kind of got scattered way out there in the little corner where you couldn't see it purposely. But we noticed that the flow would start and stop toward the end when it got down to the dribble stage. And that seemed to be related to air temperature. And when it got warmer, the flow would begin. When it got cold at night, it would stop. But that didn't happen every time. And so we had to tease out the air temperature and found out that it was related to barometric pressure. That when a high pressure area came through, it forced the water out of the soil. We didn't know those things. We wanted to make sure that the results we got and the gradient of soil moisture content was not because the bulk density, in other words, the grams of soil per cubic centimeter, hadn't changed because the soil had slid down the slope. And so Ron Hibbard went out there to take some bulk density measurements. For those who are lucky enough not to have done this, this involves digging down into the soil and driving a metal core and then carefully getting that off and weighing this known volume of soil to determine how much soil is in that circular collector. Luckily, Ron started at the top of the model, and he dug down and he took some samples, and he dug down further and took some more, dug down all the way. And this was after the experiment was over. Flow had ceased. But after Ron got done taking the first set of samples, it started up again. He had broken a tension column. If you can imagine, water molecules up that 20, 30, or 40 feet of soil were all connected, and they were pulling on each other. It's like two kids with a rubber band, and one lets loose, the other one gets all of it. And that's what Ron had done. He had cut that tension column in that soil. And it's hard to believe that such a thing even exists. The other mystical thing was Jack Shope was the forest superintendent. And Jack had reached the point in training that if there was bare soil, he got the bag of grass seed and put it on. So here he had this bare soil on top of this soil model, so he put grass seed on it. And about 2 months or 3 months later, John Hewlett went out there and he noticed that the grass was taller down at the bottom than it was at the top. And he said, "Whoa, let's go get a ruler." So we got a ruler and we started measuring the height of that grass. And we got the neutron meter out there and we measured the moisture content, and we found that there was the more moisture or the less moisture or the further we were from the water table, the smaller the grass was. The grass was responding directly to the things that we had been measuring. Wow. Well, what else did we do? Well, I mentioned that there were several soil models. There was soil model 1, wasn't big enough, so we knocked the bottom off and made it longer, and soil model 2. The next August, it's just 2 or 3 months later, we went out behind the brick building and built soil model 3, which was 3 feet in cross section and 45 feet long. In other words, we were continually finding that we had not pushed the limits of the, well, anyhow, this is model 3. We got a little smarter. We got a set of steps up the right-hand side, and I believe this model has been activated. This is the one that we got smart and covered it up to reduce the temperature effect. The two gentlemen in the picture on the left is John Hewlett, on the right is Jim Patrick, both of which are gone. But the soil model is still here. Now, soil model 4. Well, here's where we really decided we were going to push we dug a trench about 6 feet, 5 or 6 feet wide and deep. We lined it with a rug backing, then put plastic over it, taped it down with this famous red tape that we had in those days, and then filled it full of soil. It was about 200 feet long. We had the same instrumentation in it. I was away at college. I asked Ron, I says, "Well, how long did it drain?" Because that seemed to be the thing, 150 days was pretty impressive before for just 80 cubic feet of soil. What would something like this go? He says, "We got tired of waiting." In other words, the experiment never was really finished. Okay, variable source area. This was a concept that came out of this set of experiments that didn't exist before, and it kind of explained a lot of things that we had not been able to talk about, or at least to explain. On a hillside, we've got the stream, we've got the wet area next to the stream, and this wet area can expand up the slope when there's water coming in from rain and coming down the slope. But up here, we have the sort of things that we were finding with our soil model data. If you put it in the plan scale, here we have the stream, and only along the stream is it wet before the storm. As we get into the storm, we see that we develop wet areas around the headwaters, and of course the stream area gets wet. And this can get pushed further as we move into the hydrograph. And at the peak of the storm, we've got this much of the watershed contributing directly to the hydrograph. The rest of that water is going into soil moisture, which is going to appear during the dry days. Well, the fellow over in TVA heard of this, and he says, well, now this solves a problem. He'd been using the Stanford model to estimate how much storm water was going to end up in the TVA lakes, because they had to make room for that storm water by pre-releasing water out of the lakes ahead of time. And so they were using this, but the Stanford model, and the people who designed it had discovered that 100% of the rain did not appear in the storm flow. And so they put in a fudge factor, and they said, okay, 25%. They take the rainfall amount and they put in 25%, and they use that for the model. Well, sometimes that worked, and sometimes it was 15%, sometimes it was a big number. And this gentleman says, well, obviously, this percentage is going to depend upon the duration and the volume of the storm. So he made it, instead of a fixed percentage of what they called effective rainfall, he made it a variable depending on the conditions. Vastly improved the quality of the prediction of the storm flow in the TVA system. Flow separation. If we have a hydrograph, this is kind of busy, but let's look at the heavy line. Here is a storm. It has a double peak, which is always an annoying thing, and comes out here. And this is what we used to call base flow. This is what the stream had in it before the storm. And this is what it had in it after the storm. And the question was, when is base flow back? When do we get it back? What is the separation between storm flow and base flow? And by using what we had learned from the soil model, which is this dotted line here, we established a curve, straight line curve, that separates the quick flow from the delayed flow. And in the analysis programs that Ron Hibbert and Bryant Cunningham wrote, this is part of what is calculated out and produced in our printouts. And I presume we're still doing these wonderful things. And because Bryant was analyzing data for several other Forest Service experimental areas, they're using it too. But this made a magnificent improvement in our ability to talk about how much water is due to the storm and how much water is due to the water coming out of the watershed that may have been due to the storm some weeks ago. Now, Ron Hibbert's master's thesis was the time of concentration of small mountain watersheds. Time of concentration is an engineering term. If you think of a city sewer system, it's important to know how long it takes all the water to reach at some point, like where two pipes come together. How long is it going to take the water to get to that point? That's the time of concentration, because that determines how big a pipe you need to have at that point. Well, he was trying to apply this to a mountain watershed. How long does it take the water from a storm to get to the weir? And he worked 2 years maybe here. He and I were both graduate students here at the same time. And I can remember him putting his pencil down on the table and saying, well, that's it. And I said, what's? He says, it's the time of concentration of watershed 17. I says, what is it? He says, 3 months. Well, I don't know. But anyhow, it does take a long time for the water on the ridge to get to the stream. Okay, influence of soap. This is back to this previous graph here. We calculated and created an equation. And that equation essentially is in the form of flow is some measure of the soil mass times time raised to the minus b power. Now, as we went from one size model to another, this first term increased. The more soil that the water was passing through, the bigger the number, the bigger the flow. But the exponent seemed to be within statistical error, the same number. All the soil models were put on a 40% slope. So we had the idea that if we changed the slope and kept the volume the same, or the cross-section area the same, we could keep one term fixed and have the other term vary. Now that goal was never achieved, but this is some of the interesting data that Wade Nutter came out of the tilting soil model. What we did is we built a plastic box so we could watch what we were doing, put it on a hinge down here at the bottom and a cranky at the bottom that pushed it up to different angles. Filled it full of soil and stuck all these same instruments in it, and then measured what happened when it was irrigated and then allowed to drain till it ceased. And you can see right away that the difference here, as we go from a small slope of 5 degrees to a steeper slope of 25, which is a little steeper than our soil models, this water table area gets smaller and gets confined to just this small corner. And this is the gradient of the moisture content or the temperature, or the moisture tension in the watershed. And with better instrumentation, he was able to get the shape of those curves. Well, physics tells us that water is going to move at a direction normal to these lines. Up here it's going to move more this way, down here it's going to move more this way. And so we were able to define the pathway that water takes as it moves from rainfall on the upper slope down to the stream. The drier the soil gets, the less important gravity is, and the more important the moisture or the soil moisture tension is. We never did answer the question of the change in the equation, because there was several people that went away to college or took other jobs at an inconvenient time. But we did get this piece of work done, and we're able to talk about the pathway. Now, there was a person from Oak Ridge National Laboratory whose job was to model the movement of water as it moved out of the settling basins down to the Clinch River. And the question was, how many nasties are going with it? And so he was able to use this in his analysis or modeling. And another graduate student, Ron Hibbert, ran into out in Tempe, Arizona, also did some modeling based on this same sort of data. All these things fell out of a simple little question of one man standing, looking at watershed 17 and saying, how does that water get from up there down to there? And it brought a whole slug of answers that we didn't expect, a whole bunch of questions that we didn't expect, and I feel actually contributed to rewriting the textbooks on slope hydrology. Now, one of the problems that John Hewlett had when he wrote his first report is he couldn't get the American Geophysical Union to publish it. The groundwater hydrologists kept refusing it. And so we published it as a station note, research note. And that summer, after that note came out, we had 6 different groundwater hydrologists who just happened to stop by here on their vacation to see what in heck were we up to. And Dr. Russell, who's a famous soil physicist, wrote us a letter and said, "You're right. That's the way it is." So I leave it with you that you're inheritors of a piece of history that changed the world. How about that? That'll scare you. Any questions?
Thank you, Lloyd. It's great to get that background that doesn't always appear in the vault or in papers. A lot of the information you gave us, and along those lines, you mentioned that in the early days of doing this model, that the station wasn't too keen on Coweta pursuing this line of research. And I was just curious, when the station became aware of this, and like what was their response when they found out what you were up to and what the results showed?
Well, we started building the first model in May '59, and I guess it was July or August that we got around to telling him. The problem comes back to the lysimeters, and there were a lot of very expensive lysimeters built out at San Dimas out in California. And these are big boxes with screen bottoms on a scale filled with soil so that it could measure the effect of transpiration by the change in weight. The problem was that if you get down there and look at that water coming out of the bottom, each drop has to break surface tension before it can come loose. And John said, why do that? Why don't we have it move naturally through this gradation of soil to sand to rock to stream, where we don't have that problem? Well, Glenn McGinnis, who was the assistant director in charge of Coweta at the time, had experience with lysimeters. And he was firmly convinced that the damn things didn't work. And he told John so. And I can remember walking from that office down to the first soil model behind John and Glenn. Glenn was saying, but John, they don't work. John says, well, let's take a look at it. So John gave him the story, and this was just the first model. Or, well, I guess the second model. And all Glenn could say is, I'll be damned. Well, I'll be damned. He couldn't believe the significance of what he was looking at. But he recognized that it was significant because it was very different from what, and he was trying to help us save money, not to follow down the same track that the lysimeter people had followed. They had lysimeters, I think, at Coshocton also, at ARS. And they all had the same problem. There was a change in surface tension and moisture tension at that point where the water went from soil to air. And John figured a way to get around it. Thank you for bringing that up. I forgot to mention it. Any other questions? I appreciate you all being so tolerant. As you can tell, some of these things have importance to me because I was here and I saw them happen. And I am very proud to have been a part of it.
Lloyd, when did you start at Coweta and what brought you here?
Let's see now, the ARC was I was a graduate student at NC State in 55, 56, somewhere in there. And I can remember distinctly talking to Dr. Mackey, who was my major professor, and he was a typical professor. He had file cabinets, and the student would look around the piles of paper, and there was a professor back there somewhere. And he was talking about something called Coweta, and I'd never heard. I said, what's Coweta? And he says, you don't know? You're going there. And so he picked up the phone, he made an appointment for me to come up here. And my wife and I visited, and we cooked up a study for me to do for my master's thesis. And I didn't finish it that first summer, so I came back after I'd finished my classwork as a student trainee. My previous appointment with the Forest Service had been in the Black Hills. That was a hard place to leave. But I did transfer here and became permanent in 1958 and forgot to leave. Jim Vose called me in one day and he said, do you know that you've been here 42 years? I said, no. Well, he says, you're not earning any more retirement. So that's why I'm wondering. on a short whistle here. Any other?
Yeah, I'd like to say from a management standpoint, with the National Forest of North Carolina, folks are still asking these questions. You know, how does this stuff work? Just on Tuesday, I think it was, I was on a conference call and we were talking about time of concentration and some of these just things that are now kind of basic to us, but it's because of the work at this time, at your time, plus everything else that's going on with you folks. So definitely appreciate, you know, just your wisdom and the meticulousness of it all, and your devotion to hydrology and science. It's made a huge difference, and people are still talking about it. You know, these basic principles that we consider basic principles now. Fantastic. So thank you.
You're welcome. I mentioned to the rest of you, Ray's predecessor was kind of a team member. He was in management, I was in research. I'd come up with cockeyed ideas, he'd try them out and say they didn't work, and we'd find a better way. And it was a real way to push the watershed management in Nanahill and the Pisgah National Forest way ahead of where it had been. So I enjoyed the work with the National Forest. It was always a good place to try out ideas. Thank you, ma'am.
How long did it take you again to get the first paper out as a station note?
I just remember, but there was either 2 or 3 pretty heavy refusals before we just went to the editor and said, what else can we do? And he was convinced that we had something worth publishing.
Yeah, I think what strikes me is that you guys were onto something, and the scientific community, they weren't ready for it. And so
Well, we
I'm
were
so glad to hear that it was published by the Forest Service, and that was the way that it eventually got accepted.
Yes. Well, and after that, of course, we didn't have any trouble getting stuff published on this subject. But John was a very deep thinker, and he was horribly frustrated by red tape. And this did not suit him at all, as you might imagine. We tell a story about John. He was standing up at Watershed 17 looking at, he liked to just walk up there and meditate. And he was standing there looking at the watershed, and this woodchuck came up the road. Didn't see him because he was so quiet. John doesn't see the woodchuck because he was so quiet. The woodchuck got right between his feet before either one of them knew it was there, and both of them jumped. One day, John, we ate all in a room, you know, at our desks, and I can remember John picking up a sandwich, and he got an idea. And that's as far as that sandwich got. He put it down, he got up, he went out the door, and we didn't see him till quitting time. And he just had something he had to go look into. And that was the way he was. He was a very exciting person to work with in terms of conceptualization of ideas. And this is, of course, one of them. Yes, sir.
The previous understanding about the water scooting along the bedrock, where was that established?
Well, I think it was just an extension of, if it happens down here, it probably happens up here.
I mean, like which facility or university or country or research station
I think it was,
That become the standard knowledge.
that was just, that was the way it was. I don't think anybody can be blamed for it.
Somewhere in the flatlands, anyway, yes.
You know, I shouldn't be telling tales. The idea that trees use water, and if you cut the trees, you're going to increase stream flow, was contrary to knowledge in some early forest influences, that's what watershed management was called, papers. The idea was, and this was true in taught in European schools, that if you cut the trees, the sun would dry the soil out and stream flow would decrease. And usually when they went out and looked at the stream, it was running low because it was a hot, dry day. And they weren't out there on a wet day in the rain. And so the idea that when we cut the trees, we would increase the stream flow because the trees weren't using that water anymore was just brand new. Well, at the time, John made a trip to Russia as part of an exchange thing. He was told to watch your diary because somewhere along toward the end of your trip, somebody's going to steal your diary to find out what you learned. And so he kept 2 diaries. And in one he said, "These Russians really have the right idea." And he planted all this stuff that was directly opposite from what we'd found here. And then he left it where it could get stolen. And it was stolen. That was the best part of the trip, he said. But that was, that was common knowledge. That, unfortunately, there's a fellow by the name of Penman, H.L. Penman, who had invented it was a beautiful piece of work, an equation for estimating evapotranspiration given knowing the temperature and the humidity and the solar radiation and the wind. And you take all these numbers and you put them in a pot and shake them up and it comes out with how much evaporation you've had. And he based that on the evaporation pan in a large grassy meadow. And from his viewpoint, the vegetation didn't have any effect. It was just a direct water to air process. So when he read the report on Watershed 17, he wrote a rather scathing response. And it's part of our history. It appeared in the Transactions American Geophysical Union. And Hal Wilm, who was in charge of watershed management in Washington, wrote a counter response. But what Penman had done, he'd taken the weather data from Asheville and computed what the evaporation of Watershed 17 should have been. Now, you're comparing a 40 inches of rain per year to a 70 inches of rain per year situation. So right off, he had a problem. But it wasn't until we cut Watershed 13 the second time and showed that stream flow responded as the vegetation regrew. Not only it responded as it was cut, but responded as it regrew, that a friend of Dr. Penman was able to convince him that the vegetation had an effect. It was not just a inert wick that was pulling water out of the ground. So that's the other half of our world-changing history. Thank you, Metchley. I appreciate it. You're very kind.
One more question.
Yes, sir.
From me, Lloyd. So you mentioned you're talking about the flow separation and, I've read the paper on the methods and how you quote separation at some slope like 0.05 CSM per day or something like that.
Yeah, it's a real fuzzy number, yeah.
Yeah, there's some fuzzy language in the paper too that describes where that came from, but it sounds like that was that based on the soil model data? Or
Yeah.
was it-
Mhm.
Okay.
Well, let's say it started with the soil model
Yeah.
data, but it was based upon looking at an awful lot of hydrographs, drawing a line on the hydrograph page, and figuring what the slope of the line would be, and then taking an average. And I guess I'd have to give Ron Hibbert the credit for that. That was a long, torturous process. And I think probably there's a good reason the paper doesn't clearly state why it was done. Because really, that was one of those situations where trying it out is the proof that it's right. Now, you could argue that given a different climate or a different soils or a different vegetation or something, you would have a different line, a different slope of that line. And that could possibly be. But it was kind of interesting that it worked well at in Oregon. It worked well in West Virginia. It worked well in Arizona, and that would certainly be a different climate. Maybe it's because Bryant made it work. I don't know.
Any other questions? Well, thank you so much, Lloyd. This has been great. Anytime you want to come back, let us know. Tell some more stories.
Well, if it hadn't been for Randy calling me 2 days ago and reminding me, it wouldn't have been much. He provided me a great deal of support, and I'm much appreciated. He made copies of these graphs and pictures, and well, that needed to be done. We needed to digitize that stuff anyhow, but it was helpful to me.
As a student of Penman-Monteith equations, they're ingrained in me. One of the first things I remember doing when I came here as a postdoc was reading some of those AGU papers, and they're scanned on in the Coweta publications database, and I think it's your writing in the margins. If you haven't seen those, download them.
Was it something a lady could read?
I found them interesting.
There was at that point, there was a great deal of vociferousness, anyhow, anger, because people were pointing fingers and not getting anywhere.
And wasn't there, I think I remember reading this too, and I think you had written in the margins of, there's a debate about whether a grassland could use as much water as a forest, and that was part of the justification for the Watershed 6 experiment.
Yeah, we were already wondering about that. Another thing that Wayne Swank and I wanted to do is to plant a watershed with Douglas fir, so we could make a direct comparison with Andrews. And man, I guess wisely people said, you don't want to import a strange species like that. But it was a surprise to us that we ended up finding out that grass had used as much water as the trees within statistical error. And it has to do with the leaf area and the vigor of the vegetation rather than the height.